All right, let's talk about amides. So amides are our carboxylic acid derivative that has the nitrogen on it. One nitrogen and then two bonds to the oxygen. Amides are our least reactive of all of our functional groups covered thus far. So they're the most stable. And because they're the most stable, we can use any of our other derivatives to make them. So we can go from acid chlorides, we can go from anhydrides, we can go from esters, and we can go from acids. All of these can be converted into amides because the amides are the lowest energy of all of the derivatives. For these, typically you're going to need excess of your amine in order to get these to work. And of course, some heat and generally some acid if you're on the lower energy end of things. If you're using an acid chloride or anhydride, you're probably not going to need the heat or the acid in there to help things go. But otherwise, any of these can be turned into an amide. So there we have it. We have our least reactive. Of course, just like every other derivative, if we want to think how to work with these, first thing we can do is hydrolyze them, right? In either acidic conditions or basic conditions, you can get amides out. I'm sorry, you can get acids out of amides if you hydrolyze them under either acidic or basic conditions. So OH minus, H2O, heat, looks like a fun V, you'll end up getting your acid out. So just like with any of them, they can all undergo hydrolysis. And we react these, we see that there are different byproducts. With the acidic conditions, you'll end up with your protonated amine at the end. And technically, in the basic conditions, you will end up with the deprotonated carboxylate, which then you would want to do an acid workup if you want to isolate the carboxylic acid. So if you really want the carboxylic acid, you need to do your first step as the base hydrolysis, second step an acid wash will get you your carboxylic acid. And that's done in the workup of the reaction, so afterwards. So, pretty exciting, as we know. Hydrolysis is always the fun part of this. They follow the same mechanisms as all the other hydrolysis, either acid or base, that we covered last week. And so, if we want to look at other things we can do, we can reduce amides using lithium aluminum hydride. If we do that, we just need a water workup. When we do this, we actually just get the amine out. So unlike all the other times where we've ended up with an alcohol after reducing our carboxylic acid derivative, in this case, we end up with an amine. And that's going to be very useful for us in a couple of chapters when we talk about amines, because this is one way to synthesize them. So reduction of a carbonyl. And so with this, you'll want to use your lithium aluminum hydride. That's the way you're going to do it. It'll just go crazy and go ahead and break everything down back into your amine. So because amides are our least reactive, we don't really have anything else to do with them. We can hydrolyze them or reduce them. But while hydrolysis maybe is not as useful, the reduction is. And we're going to see that many of the examples we're going to talk about in the amines chapter will focus on reduction reactions. Specifically reductive amination, although that is a different mechanism here, we can also achieve amines from reduction of amides. And so with this one, I just want to close with a little notes of the properties of amides. So amides are particularly stable, right? They're the lowest energy. We often see them in polymers, although that's something we'll cover maybe at the end of the semester if we have time. What's interesting is they're the most biologically relevant of all of these derivatives, because all of our proteins are made of amino acids, and those are held together through these amide linkages. And what's important here is that we have some interesting properties when we look at an amide. First of all, amides are not basic. In fact, they're slightly acidic. They have pKa's of about 15, and they are not basic at all. So they're minorly about the same acidity as an alcohol or water. They're not bases at all, unlike amines. Amines are bases, but amides are not. And we'll see why that is in a second. And in fact, because of the ability of the amide to resonate once it's deprotonated, these are actually slightly acidic. So unlike our other nitrogen-containing compounds, which are all bases, amides are actually slightly acidic. And so if we take a look at how that looks, if we go ahead and deprotonate it, of course, the particular acidity is determined by the stability of the conjugate base. So here's our conjugate base. It can resonate just like a carboxylic acid can, giving us, single H, the following. And so it's, of course, more stable to have the negative charge on the oxygen once the resonance happens, because oxygen is more electronegative. So we have that contributing to the acidity of our amide. And this resonance actually happens normally as well, without it being deprotonated. And so this resonance that occurs contributes to the physics of amides. Amides, because they spend a relatively good deal of time in this form, because it's not terribly unstable, right? We have added formal charges, which is not a good thing. But we have octets everywhere. We have a negative on a relatively electronegative atom. We have a positive on nitrogen, but it still has its octet, so that's pretty good. As a result of this, it's actually pretty difficult to rotate along amide bonds. So we know that double bonds are rotation limited, right? They can't. And so we see, as a result of this, that proteins have a tough time rotating along this bond. We're going to see when we talk about proteins at the very end of the semester that all of the chemistry that's happening with proteins is all about the side chains. And mostly we're talking about not like intermolecular forces there. So hydrogen bonds, ionic interactions, that sort of thing. And so the backbone, which are going to be these amides, is relatively rigid because of this resonance that is pretty hard to turn them along those bonds. And so this kind of helps proteins stay in their shape once they have found it. And so we'll talk about that towards the end of the semester. So there's amides. You can hydrolyze them or reduce them. Hooray! Very exciting stuff. In our last carboxylic acid derivative, we're going to talk about nitriles.